so before I get started, I usually get frustrated when I'm diligently processing a slide and then the speaker advances. So I'd like to invite you to scan the QR code so you can have your very own copy of my slides. And then you can move through them at your own pace. And if I move too fast, then feel free to go back. I'm hoping it helps. We'll see. If it doesn't, I'm very open to feedback. Great, thanks. So, Everettian quantum mechanics is polarizing. On one hand, proponents of EQM claim to have solved the measurement problem without invoking a collapse postulate or any hidden variables, but on the other hand, the most common interpretation of Everett's formalism involves a rather off-putting commitment to many worlds. Curiously, though many of the other distasteful features of EQM, such as issues relating to probability or identity or confirmation, have themselves inspired vast literatures, the problem of ontological extravagance remains largely neglected. So I don't want to say it's the case that nobody has weighed in on this exact problem. David Albert, for instance, refers to talk of many worlds as vulgar. Mark Chilton writes, it nevertheless appears that the more extravagant understanding, namely that of many worlds, is one whose basic ontology is clearest and which provides the logically sharpest solution to the measurement problem. Malia and Franklin separately gesture toward the extravagance of EQM as a serious drawback, and Nina Emery cautions of the costs associated with a many worlds ontology. Criticizing the formulation of EQM put forth by Deutsch in 1997, Norris despairs over, quote, yet another bout of wacky metaphysical extravagance, end quote. So these sentiments are representative of off-the-cuff remarks against EQM uttered in casual settings, but there's a notable lack of argumentation in the literature. This is unfortunate, I think. The objection, whatever it is underlying these sentiments, is sufficiently strong to dissuade some non-Everettians from viewing EQM as a viable option, yet it's weak enough that Everettians have historically brushed it aside. There are multiple versions of the objection, as I'll discuss. In their haste, Everettians have failed to recognize the versions of the objection that are not immediately dismissible. And this is a shame, because it seems to me that Everettians only stand to benefit from engagement with the more compelling versions of this objection. So the remainder of the talk will proceed as follows. I'll start with a discussion of incredulous stare-style arguments that have been leveraged against EQM. These come in two flavors. First, there are those grounded in concerns relating to the overall ontic extravagance of EQM, both in terms of the number of worlds EQM seemingly commits us to, and maybe in terms of the number of postulates. The second set of concerns has to do with the overall divergence from the manifest image, or the way we generally take the world to be. So next, I'll pause to examine the state of play before assessing which of these norms are justified. Finally, I'll forecast a possible move available to the Everettian wishing to improve their ontological commitments. All right, let's begin. So neither David Wallace nor I have been able to locate this exact sentence anywhere, but David Lewis supposedly wrote, quote, I do not know how to refute the incredulous stare. In any case, the meaning of this utterance is more or less equivalent to a passage on page 86 On the Plurality of Worlds, complaining that the incredulous stare objection at its worst leads to a standoff, and that it's not really answerable, and that it's also not conclusive. So Wallace thus begins the first interlude of his book, recounting an imagined dialogue between himself and proponents of a many worlds interpretation of EQM and a critic thereof. Unfortunately, this is the most thorough and explicit treatment of this often cited objection to EQM by an Everettian. Though I want to be absolutely fair, Sean Carroll includes a very similar discussion, also in dialogue form, in one of his pop science, pop philosophy books. But instead the discussion occurs between a philosopher of physics named Alice and her stubborn physicist father. But anyway, the exchange, from the exchange we can extract this argument. Cool. So 1, Occam's razor demands that we not multiply our ontological commitments beyond what is strictly necessary. We ought to adopt Occam's razor. EQM entails a multitude of worlds, and a multitude of worlds is not necessary. So by 1, 3, and 4, EQM violates Occam's razor, and we ought to reject EQM. So Wallace initially disputes premise 4. The multitude of worlds, he argues, are necessary. The sense in which the multitude of worlds is necessary, though, depends on whether we take EQM to be true. This obviously shouldn't be especially compelling to anyone who doesn't already think that EQM is true. John Bell agrees with me, so I'm in good company. Quote, the Everett theory is simply the pilot wave theory without trajectories. Now, it seems to me that the multiplication of universes is extravagant and serves no real purpose in the theory, and can simply be dropped without repercussions. End quote. So this could spell trouble for the Everettian, plausibly. As becomes evident through the dialogue, the disagreement between Wallace and his imagined interlocutor rests on diverging interpretations of which sorts of unnecessary ontological commitments are pernicious, according to Occamist considerations. This divergence shows up in the dialogical exchange. So here's Wallace, quote, we don't tend to assume that cosmological theories are a priori more or less likely to be true according to how many galaxies they postulate. Generally, in physics, we try to keep our number of postulates and the complexity of our theories as low as possible, end quote. So from Wallace's utterance, we can extract two possible norms. First, if Wallace's imagined critic is correct, then Occam's razor tells us that we should prefer theories that commit us to fewer objects. I'm inclined to agree with Wallace, though. It doesn't seem to me that we should think that theories are more or less likely to be true just because they commit us to the existence of some number of galaxies. But Everettian worlds are different from galaxies. They're not observable, right? So, this is so much text and it's so dim. I'm sorry, everyone. Wallace anticipates the concern and he dismisses it outright, insisting that our best theory, EQM, tells us why they're not observable, and further, that if we were properly situated in the multiverse, they would be. So again, there are two ways to interpret what it would mean to be properly situated in the multiverse. One, in order to see just some other world, we'd have to be an inhabitant of that world. Or two, to observe many worlds concurrently, we'd have to occupy quite a different sort of perspective altogether, some sort of God's eye view. The former counterfactual reading is trivially true, but for that reason, it wouldn't really solve the problem of observability for the Everettian. The latter, on the other hand, makes very little sense for inhabitants of the decoherent branching structure. So I don't find Wallace's reply to his fictional critic especially compelling. Fortunately, however, it helps us sharpen the ontic comparison formulation of this objection. It's not merely that we ought to prefer theories that have smaller ontological commitments, but rather that we ought to prefer theories that have more modest commitments to unobservable objects, all else being equal. So, put more precisely, for any two theories, TA and TB, that have identical explanatory and predictive power, we ought to prefer the theory with more modest commitments to unobservable objects. I'll call this comparative ontic abundance. By contrast, Wallace prefers a norm concerned with postulate abundance. For any two theories, TA and TB, that have identical explanatory and predictive power, we ought to prefer the theory with the more economical set of postulates. So when I say more economical set of postulates, what I really mean to reference is both the number of postulates and the overall complexity of these postulates. This isn't something I'm trying to quantify very precisely, at least not at this juncture. Wallace is quick to dismiss the ontic abundance norm, claiming, quote, if you say Occam's razor rules out the Everett interpretation, you're not really making just one more application of a tried and true philosophical principle. You're appealing to a new principle, that we should reject theories according to which the universe exceeds some threshold size. And that principle doesn't have any independent motivation, end quote. So whether we should outright reject theories on the basis of the size of our universe that the theory commits us to is something different from comparative ontic abundance. This norm contains an appeal to some sort of absolute criterion. I'll call this norm the absolute ontic abundance norm, which says we ought to accept any theory T only if T ontologically commits us to fewer than n observable objects. And of course, there's an analog absolute postulate abundance norm, which tells us that we ought to accept any theory T only if T's set of postulates meets some threshold level of economy. So at first glance, we might be tempted to follow Wallace and dismiss the abundance norms outright. But in this haste would be a mistake. Here's how these norms could function in action. So consider two different scales for the application of these norms, one for intra-community judgments. So in these contexts, discussants share some prior ontological commitments. For example, these judgments might have been made at the 2022 Many Worlds Interpretation Conference in Tel Aviv, where the central question of the conference is, why isn't everyone an Everettian? But for inter-community judgments, this is a more global matter. We don't all share ontic commitments. So these sort of considerations might have taken place at the 1962 conference on the foundations of quantum mechanics at Xavier University, or the foundations meeting that's going on right now. So in local cases of application, individual researchers and local research communities might reflect and come to believe that their personal or community sensibilities around postulate or ontic abundance have been violated. In such cases, they should be motivated to seek a competitor theory, and then they should subsequently employ the appropriate comparative norm to help adjudicate between the two options. In cases of global application, the comparative norms reign supreme. This is where we might, for instance, hold up our best Bohmian and Everettian ontologies and select the better option. The problem, though, as we saw in Wallace's dialogue, is that Everettians and non-Everettians, for instance, Bohmians, seem to prioritize different values in theory choice. So we find ourselves at an awkward crossroads, where some critics of EQM are concerned with the ontological excess as it pertains to the amount of stuff posited by EQM compared to other formulations of quantum mechanics. Everettians tend to celebrate the overall economy of EQM compared to that of their competitors. Contra Wallace's assertion, there's hardly consensus on which sort of parsimony the optimist norm actually concerns. And it's not obvious how one should adjudicate between these two competing values when it comes to theory choice. In fact, one should expect different people to weigh the values of these different sorts differently. So, even if they're justified, arguments from parsimony alone can neither condemn nor vindicate EQM. For some, it might be true that EQM violates the absolute ontic abundance criterion, and this could motivate efforts to seek a more parsimonious Everettian metaphysics. It's unlikely, though, that this will lead to a widespread effort to do so. I suspect that, like David Wallace, many Everettians are happy to live with the ontic burden of many unobservable worlds. But fortunately, there's another sort of simplicity consideration that I've not yet examined. This alternate consideration concerns the overall complexity of the story the Everettian must tell in order to bridge the gap between their experience of physical reality and that which the theory actually postulates. Okay, so alas, it seems that these arguments from parsimony will not do the trick. But I want to highlight there is something about many worlds ontologies that is off-puttingly unexpected. So I'm going to develop another pair of norms, and like the norms of the previous section, one will be comparative and the other absolute. Both will concern the overall unexpectedness of the consequences associated with the theory or theories under consideration. So first, I'll issue a word of caution. That some theory has unexpected consequences does not constitute sufficient grounds for rejection. After all, instances of successful theories with unexpected consequences abound in the history of physics, even if they do tend to solicit incredulous stares at one time or another. A familiar historical example from optics is as follows. Fresnel's wave theory of light saw little uptake initially because it predicted that there should appear a bright spot in the shadow behind a circular disk. The absurdity of this prediction was mistakenly taken as grounds to reject the theory. So unexpected consequences or commitments alone should not lead us to reject a theory outright. But for many, it seems that the degree to which many worlds ontologies are surprisingly is a sufficiently strong turnoff. So this is the gist of the sort of repulsion that Emery sharpens into what she calls the minimal divergence norm. Here's Emery, quote, "Insofar as we have two or more empirically adequate scientific theories, two theories that both accurately predict the phenomena that we observe, we ought to choose the one that minimizes the difference between the way the theory says the world is and the way the world appears to be," end quote. So according to the minimal divergence norm, we ought to prefer theories that deviate least from the manifest image, or the way we generally perceive the world to be. For any pair of equally empirically adequate and explanatorily useful theories, then, we ought to prefer the theory that posits the physical reality most closely aligned with our perception of physical reality, which, as Emery notes, is made up of things like tables and chairs and trees and the like. So put another way, we perceive the world as being made up of macroscopic classical objects. For any remotely adequate quantum theory, we must be able to tell a story about why we perceive the world as we do. So if we think that the best way to do metaphysics is to first look to our best scientific theories, then it seems to me that this is a perfectly fine approach. We probably shouldn't give radical, what Emery calls radical metaphysical hypotheses like evil demon ontologies much credence at all, precisely because such an ontology would be violently at odds with our best scientific theories and our perception of the world. So we perceive the world as being made up of macroscopic classical objects, tables and chairs. So we need to be able to tell a story about why the world is as we perceive it to be. And the simpler the story, the better. So this spells trouble for EQM. It doesn't exactly say that the world is wildly different from the way it appears to be, but instead that there is much more to the world than there appears to be. Okay. I think there's a small problem with the minimal divergence norm. There's no unique way that the world appears to be, and I'm sure that this varies agent to agent, and it's certainly theory-laden, as all observations are. So for this reason, I want to sharpen the minimal divergence norm to avoid problems associated with the theory-ladenness of perception. So instead of comparing ontology according to such and such theory to the manifest image, why not compare it to the ontology of classical mechanics? So, okay, 3 worries might arise immediately. First, classical mechanics makes use of all sorts of theoretical entities that are unobservable, such as point particles and fields. And these are decisively not part of the manifest image. So in response, classical mechanics is itself an idealization, one that is so excellent that it plays a key role in, for instance, civil engineering. The chemical properties of the materials aside, I highly doubt that anything but classical concepts played a role in constructing this building, for instance. But I might be wrong. I'm open to pushback on that. Detecting the real-world counterparts to the objects of the theory should be sufficient to dissolve the worry. We can readily, often, observe the sorts of systems that we use classical mechanics to model. So there's an easy story to tell linking classical mechanics to the manifest image. For those who deeply value a primitive ontology, leaning on classical mechanics as an intermediate step can help them formalize their account. One might imagine that using something like a distance function to measure the relative difference between classical mechanics and 2 competitor theories. Right now, I'm going to propose no such distance function, but to be honest, I'm at a loss for how one would even begin to write a similar distance function if the manifest image is the point of reference. So here's a second concern. Of all the available theories, why look to proximity to ontology according to classical mechanics as our guide to metaphysical theory choice? After all, classical mechanics could have easily been some other theory altogether. This objection also doesn't especially worry me. Classical mechanics has an obvious primitive ontology, and it's the predecessor theory to quantum theories. And as I just mentioned, it's enormously useful in our everyday lives. It works really, really well. All right. So finally, classical mechanics has no singular unique referent. We have theories of like particles or continua, etc. So I think this should really worry the person who's married to the idea of writing an authoritative and precise classical distance function, because then they would need to choose some formulation of classical mechanics to rely on. But for concerns relating to the divergence between the ontic-commitments of classical mechanics and the Everettian, I strongly suspect that the differences between these various formulations of classical mechanics are negligible. Probably. I haven't worked out the details of it. But I think it's in our best interest to make modest modifications to our ontic commitments to help us avoid taking on unnecessary ones. This is not to say that our ontic commitments will not shift as our best scientific theories evolve, but I just want to say that we should be a bit conservative about such matters. Or at least that's what the norm says. So with those issues dealt with, we find ourselves with 2 additional norms for theory choice. Absolute classical divergence, which says that we ought to accept some theory T only if the difference between the way T says the world is and the way classical mechanics says the world is falls beneath a certain threshold. And comparative classical divergence. So for any 2 theories, TA and TB, that have identical explanatory and predictive power, we ought to prefer the theory that minimizes the difference between the way the theory says the world is and the way classical mechanics says the world is. So now we have this nice little taxonomy of simplicity considerations. At this stage, I'll review the state of play. So it's difficult to know how to definitively apply comparative ontic abundance and comparative postulate abundance to either condemn or vindicate many worlds' ontologies. And I think this is probably why there's been a communication breakdown, at least along this line, between Everettians and their critics. And it's not totally clear that we should accept any of these norms. So you might wonder, are any of them justified? So let's start with the comparative postulate abundance norm and compare it to an analogous norm in scientific inquiry. After all, scientists and metaphysicians are both interested in what the world is like, so it would be unsurprising to me if they were to share some of the same methodologies. Now, simpler scientific theories, or scientific theories with simpler sets of postulates, stand a stronger chance of confirmation. They're just easier to work with. But as Mary Beth Willard argues, there's no real sense of confirmation in metaphysics. So I'm not sure this sort of argument will do. Now, in the history of science, there's a pattern of simpler theories replacing complex theories. So for instance, remember from your introductory astronomy, we saw circular orbits plus epicycles on epicycles being replaced by elliptical orbits. But unfortunately, there's no similar sense of progress in metaphysics. So many of us find simplicity a la postulate abundance aesthetically pleasing, but I think that this lacks a normative punch. I also think I should be quite transparent here. I started work on EQM because I found its simplicity really beautiful. So at best, we could adopt this norm in order to attract others to work on our theory of choice. So maybe there are good reasons to adopt postulate abundance norms, but they seem a bit weak. So I fear that the ontic abundance norms don't fare much better. Let's again examine the scientific analog to the comparative ontic abundance norm. It's reasonable to think that if some scientific theory TA is identical to some other theory TB, except for some bonus ontological commitments to entities that play no explanatory role, we really should favor TB. It's easier to confirm. If there are extra bits to the theory, it will, of course, take more effort to confirm that those extra bits have some role to play. But in the case of metaphysics, there's once again no relevant notion of confirmation. So it's not obvious to me that this norm should apply in cases of metaphysical theory choice. But okay, yeah. Of course, it's possible that once again, ontic abundance norms are really aesthetic in nature. But as before, this fails to carry the normative punch that I really want it to. Though, maybe it's a good way to attract colleagues. So let's move on to the classical abundance norms. Nina Emery observes that historically we have tended to prefer metaphysical theses that do not wildly contradict our common sense. But even if we have historical evidence of this, this is a description of our preferences. And there's no reason to think that this norm is truth tracking. So, should we continue to prefer such theories? Nina says yes. She argues that we should with an inductive argument. This has worked in the past and it will probably continue to work in the future. You can imagine that if we were to take an evil demon ontology seriously, we might be disinclined to continue our scientific inquiry, unless we cashed it out as like seeking the demon's book of the world or something. But I don't think there's any reason to think that this norm is truth tracking. Or I haven't seen an argument for it, and I certainly haven't developed the argument yet. It would be really nice if I could, maybe in the future. But there might be other reasons to adopt the classical divergence norm. It might be that this sort of norm could help research communities organize themselves and conduct their inquiry more carefully or more systematically. So even though there's no sense in which there's global progress in metaphysics, it's certainly the case that individual research communities build on existing work over time. So I'm going to make a proposal for a way that metaphysical inquiry could be guided over time by drawing an analogy to Lakdash's methodology of scientific research programs. So the identity conditions for any given scientific research community consists of the hard core in the yellow, the immutable identity conditions for each community. Surrounding the hard core is a protective belt that involves the peripheral commitments that can change or evolve over time through inquiry. So this account both describes research communities and it also tells us when they're degenerating, when the core commitments or the hard core begins to degenerate or erode. Research communities in naturalistic metaphysics, I think, also have hard cores. which also consist of the immutable identity conditions for each community. So for instance, Everettians all agree that the universal wave function is the most fundamental description of reality. One can imagine that the projective belt could be partitioned radially, where each segment on a particular coarse graining corresponds to a subcommunity that holds some secondary set of commitments. And those commitments provide the identity conditions for that subcommunity. So by minimizing the distance between the set of ontic commitments of the shared predecessor theory and the new metaphysical theories, research communities should be able to avoid committing themselves to unnecessarily radical revisions to our ontological commitments. So in order to put their best ontic proposals forward, sub-communities should work to minimize classical divergence while preserving their unique commitments before invoking the comparative classical divergence norm. One might imagine, for instance, that the Everettian subcommunity of quantum modal realists could use this methodology. Within this research community, members commit themselves to the existence of a multiverse containing an ensemble of non-overlapping worlds, each just as concrete as the others. Given this commitment, modal realists could then seek an Everettian ontology that outperforms competitor quantum modal realist ontologies. Only then should they apply the comparative classical divergence norm in order to compare the best version of their ontology against other Everettian ontologies. Should the core assumptions of the subcommunity begin to erode, this would suggest that that subcommunity degenerates and vanishes. And then once the Everettians have identified a strong Everettian ontology, they should seek to compare their ontology to non-Everettian ontologies like GRW or Bohmian mechanics or whatever else. So I want to be clear, I don't think that this norm helps us select theories that are more likely to be capital T true, or at least I haven't argued for that yet. But I think this norm can at least help us more carefully explore possibility space within our research programs. You might worry that the story I've told assumes some sort of rosy optimism about convergence on a single ontology. Alternatively, you might fear that in the absence of the convergence on a single ontology, Everettians will never reach the point of applying the classical abundance norm to adjudicate between their best ontology and that of their competitors. And obviously this would not improve the state of affairs, but fortunately this need not be the case. This methodology should accomplish the following. 1, it will allow Everettians to rule out possible ontic approaches as the research programs of their subcommunities degenerate. 2, it will allow Everettians a way to reason about competitor ontologies. And 3, it will allow Everettians to reason more carefully through possibility space, and it will help them avoid adopting unnecessarily radical quantum ontologies, e.g. those ontologies that deviate more than necessary from those of the predecessor theory. All right, so what's the Everettian to do? According to the classical divergence norms, EQM is problematic just because it seems to commit us to a many worlds ontology. Classical mechanics, on the other hand, does no such thing. So let's take a look at the formalization of this objection. 1, ACD. We ought to accept any theory T only if the difference between the way T says the world is and the way classical mechanics says the world is falls beneath a certain threshold. 2, any theory that entails a multitude of worlds exceeds the above mentioned threshold. 3, EQM entails a multitude of worlds. And 4, we ought not accept EQM. So I expect that many Everettians will take issue with premise 3, but making that move only promises to extend the communication breakdown between Everettians and those who prefer other approaches. So instead, I encourage Everettians to challenge premise 3. If it's possible for the Everettian to make do without a commitment to many worlds, this would be an ideal place to begin minimizing classical divergence. Thanks.
Now the floor goes to Hubert with his comment.
Here we go, great. So thank you for having me commenting on the paper. The paper is very nicely written, so I actually only good things to say about the paper. First, the way the arguments are presented, the way it's structured, and also the kind of path is actually taken. So what I want to contribute in these comments are more like certain kind of ideas, things where the paper can say something more, and maybe giving a little bit of a different context, but overall I'm very close to what Ray actually wrote in the paper. So the central question that this paper addresses is what's wrong with the many worlds in the Everett interpretation. That's for some reason a question that is not so much discussed in the literature. So there are a lot of other problems, like the problem of probability, the problem of how we can justify certain observable objects and things like that, but not so much the issue of the abundance of many worlds. So there's an intuitive reaction. You may say, okay, actually many worlds are bad, and you have some kind of an intuition that we should have just a theory that postulates one world, or they're kind of cool. This is something that I was, as a student, very intrigued to understand in many worlds, that it postulates these different other worlds that we cannot access, but they're somehow there. So the paper wants to make it more precise in what way we can accept or not accept the different worlds that are actually introduced in this quantum theory. So you may have actually two routes doing that. So one thing is you may give guides to truth and say, I have a certain kind of procedure that tells us, yes, these worlds actually exist. And one would be something like empirical adequacy, or that we have some empirical means to test that. The thing is just that with going that route, standard quantum mechanics and many other quantum theories are equally empirically adequate, and there's no way to say, here's an experimental procedure that really confirms only the worlds and not the other parts of the theory, or the other parts and the worlds. So that's a route that doesn't really work. So the paper takes a different route, namely, it wants to give guides to theory acceptance. So given that we have this quantum theory, on what kind of theoretical or metaphysical or methodological grounds can we accept or not accept these many worlds. One principle that is spelled out in the paper is a more precise version of Occam's razor. And the second kind of route that is introduced are some coherence conditions between the manifest image and the scientific image, especially the coherence condition between what many worlds tell us how the world is, and classical physics or the classical manifest image. Good. So I want to comment briefly on exactly these two guides, namely Occam's razor and the coherence conditions. So let me start with the Occam's razor that is targeted to the Everett interpretation. Good. So you have in different physical theories unobservable entities, and in many worlds there are these worlds. You don't have really empirical access to them apart from the world that we are actually in. You don't have empirical access to the others. But they play a role, so they're not like arbitrary or just some artifacts or so on. They have a role in explanation, and namely, they explain the macroscopic, or that we don't see macroscopic superpositions. And in some way, that's kind of natural to have these many worlds, because all the different branches are on an equal footing. No one of these branches is actually privileged. So there seems to be a natural reason to say, okay, if the theory describes how the world is, there's a good argument why we should, or why these other worlds actually exist. I want to contrast that to particles, because if you just say, okay, we just count different unobservable entities and we just count the different worlds, then we can say, oh, let's just count particles, and these particles are also close to infinity, and we cannot directly individually observe them, so why should we believe in particles? So it's not the kind of parallel counting argument that you can apply to many worlds and to particles. In some way you can then argue and say that the particles are more observable, accessible, because the way that theories like classical mechanics or bone mechanics explain what particles do is that we can, in a certain way, either indirectly or collectively observe them. So there seems to be a certain kind of asymmetry, and Jeff Barrett has a nice paper that explains in more detail how this observation works. That is it's interesting to see that in bone mechanics it's a bit more indirect than in classical physics. Good. The paper also mentions Everett question mark theory. That was in some way not developed or just postulated by John Bell in a little bit to make fun of quantum mechanics, or of Everettian quantum mechanics actually, because for John Bell the problem is that local variables are essential for physics. So if a physical theory that does not have in some way local variables, then it's not an acceptable physical theory, because it does not explain how we can observe the kind of local objects that we deal with in everyday life and then also in physical experiments. So for him, actually, the many worlds are not the problematic issue. The problematic issue is that the many worlds theory does not introduce these local variables. So therefore, this picture of just something like the wave function evolving is not sufficient, because there's a disconnect between the theory of ontology and what we observe. In Bohmian mechanics, we have the same kind of wave function structure, but one of these branches is then privileged, because this is where the particles are, and the others they are empty. But on the level of the wave function, the theories are equivalent. So Bell said, okay, I postulate another theory that he calls a question mark. It's like Bohmian mechanics without trajectories, and the idea here is there's just one dot that is like the universal particle that is then jumping stochastically, and then it will trace out some path like that, and it just goes on. I was just too lazy just to do the whole thing, but it's just one particle that goes like that. And therefore he said, okay, actually the Everettian quantum mechanics is indeed something like Bohmian mechanics in denial, and then we know the other argument by Wallace and Brown, the other way around. So good. So here, because of that, I want to just hint that maybe one can make an argument stronger for many worlds, that there are different versions of many worlds. It can have like wave function realism, like decoherent histories that Wallace spells out in his book, or some form of space-time state realism that is almost local variables, but not really. So you may say maybe these many worlds are getting a bit more acceptable, given that we put some different structures in there, and they come a little bit closer to classical physics or something like that. So very briefly, I want to say something about classical physics that is also very important in the paper. So one sentence or one idea that the paper spells out, that the manifest image may diverge dramatically from agent to agent. So therefore, actually, we should not use the manifest image for our scientific reasoning, because it's too divergent and so on. I think you can just narrow that down and say, yes, in some way that's right, but for the scientific purposes, we don't need to have, the entire manifest image with all kind of diversity, but only certain kind of maybe stable features that are that we can agree that most of the agents actually agree on in the manifest image. And then the scientific image can be diverge dramatically, given the kind of theory that you have in mind, or that you think is the best. At the boundary somehow, is it the boundary of the scientific image or the boundary of the manifest image, there's somehow classical physics, a classical scientific image or something like that I think is important, and I like that the paper spelled this out in this comparative classical divergence criterion. And I think it's important because classical physics, it was there before quantum mechanics, and it's so successful, we still use it. It's still relevant, in some way it's superseded, but I think it's right that there has to be certain kind of consistency conditions between classical physics in some way and quantum theory or any other newer theory. I think the paper can be there a little bit more precise in saying what exactly are these features of the classical scientific image that we need to preserve in theory change. So for example, I just write down a little bit of these requirements, or something like objective world realism. Is that the thing that we need to preserve? That's an objective outside world in which physical objects have properties independent from being observed. Then a single world process, is that the important thing? Is the definiteness the important thing through the three-dimensional fundamentality, so that the fundamental physical space is three-dimensional? There's something like temporal locality, that the physical interactions travel with finite speed, they are not instantaneous. Or spatial locality, physical changes from one space-time region to another are mediated by continuous changes between the space-time regions. Causal order, and so on. And so that there's certain kind of ingredients in our classical manifest or scientific image that are somewhere around, that I think are in some way stable. And the thing is that, can we narrow that a little bit down, make the debate a bit more precise? What needs to be preserved in theory change from a quantum theory to explaining a manifest image or something like that. Great, thank you very much. These are my comments.
30 seconds. Okay. Cool. Thank you so much for the comments. I found it, I don't think I have too much of a response, but I found it really, really helpful that you spelled out all these various ways we could look to minimize classical divergence. Because this gives me a plethora of different avenues to pursue, because previously I've been only thinking about the commitment to a single world rather than many worlds. But there are clearly many different ways to go. So yeah, thank you so much. It's awesome.
We have 15 minutes for K part. Awesome. Okay. Okay.
Thanks for that. I think it was great. I have a question on the minimal divergence norm. I'm just wondering whether one might object to the minimal divergence norm by saying, well, there is something a bit. If you follow this norm, it means you are giving a lot of weight to the manifest image. But anyway, we know that the manifest image can be underdetermined, right? Many situations where the manifest image is compatible with many different options. So I wonder that maybe something a bit misleading to try to keep your scientific image as close as possible to the manifest image, because we have learned from science that it's kind of deceiving, and we should be really we should worry a bit that we should not be deceived by its structure. Right? We have to explain why we have the manifest image we have, but should we be using this kind of metaphysical structure, maybe just one word, as some kind of constraint? I mean, to me it feels a bit like there is something dangerous epistemically in following this divergence norm.
Yeah, I think I share your concern, and that underlies my motivation to sort of sharpen it into something that's more easily applicable at the very least, or more scientific, perhaps, or something closer. Well, it is the ontology according to classical mechanics is like a scientific image rather than the manifest image. But I mean, my thought here is like very basic. What we have access to through our senses amounts to the manifest image, right? The manifest image is a scientific, according to like Sellers in the 1980s, is a scientific image of sorts, just one that prohibits unobservable objects. So I take that to be the world as we perceive it. But you're right, it's a bit underdetermined, hence the attempt at precisification.
Yeah. Thanks, Ray. That was super interesting. I'm glad you reminded me of that David Wallace explicitly gives some reasons not to pay attention to ontological extravagance and not into Lugano. he also has this other argument in the main text of the book earlier on, that kind of the only game in town argument. You know, there's really, and the Everettians say this all the time, there's really only one interpretation and it's many worlds. Yeah, you could try and be a Bonian, or you could try and be a collapse theorist, but those don't really work, you know. You can't extend them to quantum field theory or whatever. So what do you think of the prospects of that kind of argument? As an only game in town argument sure, it's extravagant, but we haven't got any choice.
Sure. I'm sympathetic to that argument. I think it's really important that the quantum theory that we endorse is compatible with quantum field theory. And I worry that the immediate move to commit oneself to the existence of many worlds is mistaken. And all I'm saying is we should proceed more carefully. I think we can be Everettians. I won't argue this here, it's a separate paper, but happy to discuss after the Q&A. But I don't think there's a reason why we should automatically, as Everettians, be like, ah, yes, it is a multiverse.
Okay, so it's kind of, so that you'll suggest right at the end, we can be a one-world Everettian.
Yes.
Yeah. Okay, cool.
You can have without class. Yeah, no,
Me?
The argument, this is an objection to your question. How do you prefer to think about observability?
Whoa, that's a really good question that I haven't given any thought to. Beyond, quite basic things. Like I alluded to sense data. Of course, in physics, we rely on much more than immediate sense data, right? I don't have anything. I don't want to continue stalling because I don't think I have anything super rigorous to say. But it's worth thinking about if I want to sharpen the motivation to rely on the manifest image stuff.
Yeah, please.
Yeah, thanks, Ray. I think you agree with this, but I'm not sure about the David Wallace quote that he says something about like the size of the universe. That's a different principle. You shouldn't. We are imposing a new principle by restricting or by objecting to many words on the basis that it's making the universe bigger or something like that, right?
Mm-hmm.
But I think maybe this is part of your take, but maybe not. I think that's kind of a very strange or maybe even unfair thing to say, because it's not just the size of the universe. If you were adding empty space, people would be less worried. You are increasing the number of things in that additional part, I guess. Or, I don't know. I just felt like the Occam razor, the way he handled the Occam razor was a little maybe disingenuous, but maybe, maybe think something about that.
Yeah, I think I agree with you. And then when we're doing metaphysics, I don't know that there's like independent motivation to reject theories on the basis of how many things, like unobservable things, they commit us to. So in the end, I think I agree with his rejection, but I think it's a bit too quick. And there are certainly many, many people who take that sort of approach to Occamist norms. So it's not that it's just out of nowhere or something.
Thank you so much for this. This is really interesting. So I wonder, obviously Wallace in that same book that I think has been spoken about before, has all this kind of real pattern stuff to deal with macroscopic ontology. And I was wondering, why is it that, for example, Wallace's treatment of getting macroscopic objects, kind of special science ontology, by kind of coming up with functionalized special sciences to pick out real patterns in the quantum state. How far does that go towards alleviating some of the concerns of kind of macroscopic realism and kind of the appearance of a one world or something like this? And why is it, what's still lacking about that kind of real patterns approach for your kind of works?
Yeah, good. I sense that David Wallace, his approach is similar to that of Al Wilson, where the claim is that that which is fundamental is this universal wave function, and everything emerges from the universal wave function, so any apparently extravagant ontology just comes for free, and it's not a concern anyway. But whether or not that is true, it seems to be uncompelling to the broader quantum foundations research community. And so in order to avoid prolonging this standoff or communication breakdown, it's worth at least poking at this possibility, I think. Okay.
So next, Christian.
No, that was my question. So.
Oh.
And you already replied, so okay.
Yeah, please.
Yeah, thanks for the talk, very cool. I had a follow-up on Sebastian's question about the Occam solution given by solutions to Occam given by Wallace. Have you thought about, or maybe you did, about looking at people who are recently discussed the Occam presence in the metaphysics? Because there is this discussion about reformulating the Occam principle, not in general, but in terms of fundamentality. So the idea would be Schaffer, that's the from John Schaffer. He says something like Occam resonance in general in a vacuum doesn't mean anything. What we should not multiply without necessity are just fundamental entities. So I'm very sad of doing the job for Wallace, but what it would say is that here we're not multiplying fundamental entities, right? We're multiplying derivative that provided, I mean, not every Everettian can say this, but I guess some could say this. So this could be a way, a different way to take relative interpretation.
Yeah, I find this approach compelling. I fear that people who are not sympathetic to EQM probably will not, though.
I'm not moved by this kind of argument, but I think it's a step forward.
Yeah.
Maybe.
Worth poking at more. Yeah, thank you.
Thanks, that was a great talk. I'm worried that I'm just going to recapitulate something that was said in the commentary, but I wasn't 100% sure that this is what was being said, so I'll say it anyway. The way I understood the central point of the talk was that, even if you're sympathetic to this minimal divergence norm, it isn't really a genuine point of departure from the manifest image of classical mechanics or whatever, that there are many worlds according to EQM. Why? Because EQM doesn't count many worlds, so it can't be a point of departure from the manifest image of classical mechanics. But it basically just seems to me that there were some obvious points of departure that it's less easy to deny that EQM commits one to. So it seems like EQM says that there are, in some sense, they can be precise, no unique outcomes for experiments, quantum experiments. That seems to me to be a pretty radical point of departure from manifest image classical mechanics you want to go with. Similarly, it seems like part of the manifest image that stuff like tables and chairs are built up out of local bits of matter. And again, I think it's less easy to deny that EQM has the consequence that they're not so built up of local bits of matter. And yeah, so I was wondering whether the talk focused on a point of divergence that one can deny, maybe should deny if one is into EQM at the expense of ignoring other points of divergence that are less easy to deny, and that could well trigger this minimal divergence norm to favor another interpretation.
Yeah, absolutely. I have this charted out as a chapter that I'll work on in probably 18 months, where I think that EQM commits us to some sort of quantum indeterminacy that is like metaphysical, that can't be dismissed as like merely semantic or something, or some consequence of our language. But I don't have the arguments worked out there. But I want to argue that
no unique outcomes.
Yeah. I want to argue, since forecasting the future, that whatever costs are associated with that particular divergence are well worth the benefits of adopting EQM, such as, for instance, EQM it's compatible with quantum field theory, I said earlier, where some other approaches seem to fall flat. So the only game in town anyway. We just may as well make it as great as it can be.
And same response to the other point of the is to take it.
Yeah.
Claudia, anything on this? Or have you put any questions?
I can answer something. Yeah. Actually, my question was Kristen's question. So, but maybe I want to push a bit further at this point because, I mean, I don't see. I mean, in general, when I think of simplicity, I think of some in metaphysics, some structural ontology, and then we ask for simplicity in the fundamental structure, right? Because we want to recover the rest. So we are not really asking for simplicity in the emergent structure. As I see Everettian mechanics, you have a very simple fundamental structure, which is the universal function, and then the many more structures emerging. So it's not really a problem from this point of view. But now we say, okay, you have to accept something like a structural ontology and this emergent fundamental distinction. But I don't see, if you don't accept that, I don't see how you can apply simplicity for first selection, right? In the sense that what do you mean that you are gonna, if you have everything on the same level, right? You don't have this distinction between fundamental and non-fundamental. Okay, what do you mean by simple in that case, right? You mean that the things that are not part of the ontological committed by simplicity, they don't exist? It's not clear. Because, I mean, if you think of simplicity in the formal languages, you just apply simplicity in the axioms, right? And then if you want to derive the rest, you have to have all the expressive power that have the theory with more axioms. I think that the metaphysics could be the same. You want simplicity the fundamental, but then you want to recover the rest. But if you don't have this distinction, then I don't see how simplicity can be applied.
Okay. I want to make sure I'm understanding your question. Is it the case that you're concerned that we can't apply simplicity considerations to multiple levels at once of emergence or fundamentality?
I mean, yeah, I mean, in some sense, I would say that whoever is committed to something like simplicity is gonna apply to a part of the theory.
Yeah, sure.
Part of the axiom or part of the fundamental, right? You don't want to apply simplicity in the rest. You don't want to see the rest of things doesn't exist. I mean, in general, if you are reasonable, you don't want to see that. Okay. Then, if you don't have the distinction between fundamental and emergent, and then as Everettian, they have it. I don't know how you can apply simplicity in other cases in which you don't accept the distinction.
Yeah. Okay. So one, I want to gesture toward a little quip by Mary Beth Willard that says basically whatever sort of simplicity someone prefers or whatever method of applying this simplicity criterion that someone prefers is ultimately going to privilege their theory above others. It's part of the reason I'm a bit skeptical about the application of these simplicity considerations in metaphysical theory choice specifically. So yeah, I think I share your concern about applicability. And that's why I want to really sharpen this classical divergence set of norms instead, because I think they're more easily applicable. Potentially, I hope. It's a hope right now though, transparently.
Okay, thanks.
Yeah.
Okay, we have to stop here because time is up. Please join me to give thanks again for speaking.